Okay, so lastly, we are going to discuss Fisher projections. So this is a version of how you write out chiral molecules. So specifically, these are going to be used for our carbohydrates and sugars because it helps simplify the drawings of these molecules. So it's known that when you're drawing a Fisher projection, that even though you're drawing it in a 2D representation, that you still have chiral centers there, and it is a tetrahedral molecule. So this is a simplified system for drawing stereoisomers, which shows the arrangement around each chiral center. So you're going to start, the top of the structure is going to be the most oxidized carbon. So your carbonyl is going to go all the way at the top of your Fisher projection. Vertical lines are bonds projecting backwards from the carbon. And then the horizontal lines are bonds projecting forward from carbon. How I like to remember this, don't ask me why, but I did gymnastics growing up, and this is how I remember it. So if I think about a Fisher projection as my body, it's easy for my horizontal lines, which are my arms, it's easy for them to go in and give someone a hug. And so the horizontal lines are going forward. And then because I was a gymnast growing up, I really always loved doing back bends. And so the vertical lines go back like you're doing a back bend. So horizontal lines giving hugs like your arms, vertical lines going back in a back bend. So let's do an example. We're going to transform this molecule, which is glyceraldehyde, into its Fisher projection form. So what we're going to do is I'm going to go ahead and circle. So this carbon atom here is going to be at the top of our Fisher projection. So I'm going to draw my carbonyl with my aldehyde, and I'm going to draw just a straight line going down. So every intersection is going to be a carbon. So let's go ahead and number our carbons so we know how many carbons we're going to have. 1, 2, 3 carbons. So I have 1 here. I'm going to make a line. That will be number 2. And then my last very ending right here is going to be carbon number 3. And then I'm going to fill in what we have. So really what I'm doing is I'm taking this molecule. It's kind of hard for me to show you on video, but I'm taking this molecule and I'm going to grab it with my hands and straighten it out towards me. So the carbonyl is kind of going to go towards the back so that I have a carbon. We're going to flip it all up. So the carbon chain is going up and down. And then I'm going to use this to show what things are going on which side. So right now I have the oxygen on carbon 2 is coming out towards me. So if I grab that molecule and I lift it up and turn it towards me, that oxygen would be towards the left. So this oxygen here would go on the left on carbon 2, and we'd have a hydrogen on the right. And then carbon 3, all it has on it, it doesn't have a chiral center. So we don't need an intersection there. We just need to write CH2OH to show that orientation. You can also draw the enantiomer of this. So I'm going to draw this right here. This kind of is the universal organic or biochem way of saying mirror plane. It's drawing this kind of 3D mirror in the plane that you're talking about. I'm going to draw the other enantiomer. Which would mean that my OH is going to be on the right instead of the left. We still have 1, 2, 3 carbons, but now my OH is going to be on the opposite side. Okay, so it's pretty difficult to take what the structures we've been drawing, such as this one here, and to put them into Fisher projections. So for this course, we're primarily going to just be using Fisher projections for our understanding of sugar. However, you should be able to convert trioses, so specifically aldotrioses, to their Fisher projection. So just like what we just did. I also have this little note down here. It says use the OH group on the chiral carbon furthest from the carbonyl. So the bottom carbon that's chiral, to determine whether it's L or D. So I am going to look at, actually, let's do that. Let's do this next example and then we'll talk about that. So we have a Fisher projection here. Let's go ahead and determine whether it is L or D, and then we're going to draw the enantiomer. And then for both the glyceraldehyde and erythrose, we're going to label with whether they're D or L. So the chiral carbon furthest from the carbonyl. So we have 1, 2, 3, 4. So carbon number 3 is going to be my lowest chiral carbon. And I'm going to put a box around the oxygen or the alcohol. That alcohol is on the left side. Therefore, this is L erythrose, which is the name of this molecule. Let's go ahead and draw our enantiomer and show that it's the opposite. So we will have our carbon, carbonyl going down. And we're going to just flip everything so that it's exactly opposite. So the things that I like to kind of go like closer to the mirror and then further from the mirror so I don't get confused. So the closer side to the mirror is both hydrogens. The further side to the mirror is both oxygens. And now when I'm looking at this one, on the right side of the carbon furthest away from the carbonyl, that's chiral, it's on the right side. So then this is going to be D erythrose. Erythose. Oh, I forgot the R. Oops. So let's go back up to the top and classify these. So the reason I paused for a second was because in these aldotrioses, the most chiral carbon that's furthest away from the carbonyl is really just the one below it. And so it wouldn't have been as easy to understand. So this one would be L because it's on the left side. So it'd be L glyceraldehyde, and this would be on the right side. So it would be D glyceraldehyde. Okay, so let's do some practice of Fisher projections and chiral molecules and everything for section 2.